with Blue Coat Norway, developing behavioral malware analysis and back-end systems used to create an extensive threat intelligence collection system. Whenever that is not challenging enough, he delves into the depths of structured languages for cyber threat intelligence representation, honeypot development, and researching ICS SCADA threats under the umbrella of the Honeynet project, for which he also serves as a member of the board of directors. His specialties include problem solving, honeypot deployment, data analysis, sandbox development, and botnet monitoring. How are we doing? We close? Oh, you need credentials. Oh, okay. Yeah, we can do that. You're up.
Okay, can you hear me? Perfect. Okay, so I'm going to briefly introduce a system I'm building at Blue Coat. It's basically, we get a lot of samples and we want to analyze the samples as good as possible. Quick introduction about myself. I'm a software engineer. I'm working for Blue Coat in Norway. I'm building honeypots since 2009. I'm a member of the board of directors of the Honeynet project, and I'm working as a developer at Blue Coat. I'm not going to show a lot of bullet points and text on my slides, so you should listen to me, but I have some nice pictures. So a quick story time, how we ended up building the system. So when I started 4 years ago working at Blue Coat, back then it was Norman, which was a Norwegian AV company, we were building signatures for samples that we consider to be malicious. And if you've ever worked in the AV industry, then you always know that you're lagging behind because you have to wait for the sample to come in. You have to have someone who analyzes the sample, or you do some clustering to find out, okay, this is part of a known family. Then you create a signature, which is usually a string or bytes, a section of bytes in the binary that you consider to be an identifier for this specific sample. And then you publish that signature for your customers, and then you have detection. But this takes some time, and during that time, everyone gets infected who sees that sample and has no updated signature. And if you've ever seen those graphs, how many samples we see that are new every day, it's usually something logarithmic. It's not that true, but it looks scary, and it's a lot of samples, and it's basically impossible to keep up in a good way. So AV companies started to have reputation services, so they know in hash, if the hash is known to be malicious, then the hash either ends up in a signature file, which makes the signature file hundreds of megabytes, or it ends up on an online service, which means that your AV product will constantly go back and forth, like, hey, have you seen this MD5? No. Have you seen this MD5? No. Or, yes, I have seen it, and it's malicious, and please stop executing it. So it's not an easy thing to solve. Back at Norman, we started building a sandbox. So everyone has probably heard about sandboxing. It basically means you take a sample, which you don't know if it's bad or good. You execute it in a controlled environment, and you look how the sample behaves. So the trick is that no matter how much encryption they use, or packing, or whatever they try to hide from an AV product, it kind of gets defeated by executing it, because that's the purpose of the file. This purpose is to be executed inside the target and then do something malicious. And something malicious could mean exfiltrating data, stealing something. Nowadays it's encrypting files and then asking for ransom. So, but this has to happen. And if you execute it in a sandbox, and the sandbox is well customized, so it's impossible for the sample to detect, okay, I'm in the sandbox, I'm not doing anything malicious. If that is possible, Then you will see the malicious behavior. You can say, okay, this behaves malicious, so we detect it as a malware and protect the customer. So we had now the sandbox and a lot of samples coming in. And by a lot, I mean usually around 1 million or increasing nowadays per day. And if you want to run a sample, it takes some time. And executing something in a virtual environment takes resources. So if you run a VM on your laptop, you know it will take up a couple of gigabytes of memory. It will take up a lot of CPU cycles to boot Windows and execute a sample. You have to run it for a certain time because the sample probably downloads first something, a dropper, a different executable, and then maybe it waits just because it can. So you have to run it a certain time, and during that time you cannot run another sample inside the VM because they could interact with each other, they could block each other, or they could taint the result for one sample. So the problem is, first, how do we filter down the amount of samples we see every day to what we want to actually analyze? And that's part of the whole project. So then we started building up this whole system. It gets more complicated, it gets more hardware, it gets, it's quickly running out of control. We had enough hardware and resources to build it, but controlling it and making sure that every sample that goes in gets a verdict and ends up either in our reputation system or in a signature or in a pattern. So a pattern is a definition for malicious behavior. So this whole system was built, and I hope I can give you a short introduction how it works and give you some ideas how you could build it yourself. This is nothing that's specific for Blue Code, and you have to buy Blue Code stuff. I mean, I would love, and my company loves if you do so, but you don't have to. You can use open source products to build the same system. So samples, the problem with samples, when they come in, they come from different sources. The most popular sources you probably know is VirusTotal. They get a lot of samples from random sources, and you can pay them, or if you have an AV engine, you can get them for free. You get also samples from them. There's also other sources. There's Malware domain lists, all kinds of shady domains where you can download also samples. The problem with samples is you have zero control what is coming in. Even if you subscribe to VirusTotal, you don't know what is coming in. You have no control. It could be that for one day you only see ransomware, because that's what VirusTotal got. So all of a sudden you see a spike in ransomware, and you see, oh my God, something is going on. But it was just an AV company in Germany deciding, okay, now we have this big selection of ransomware, or we forgot to upload it to VirusTotal, and they do it in one day. That kind of screws, and you have to be aware that there's nothing in control. Everything that comes in is random, and you have to control it by yourself. So what we use for analyzing the samples is the Malware Analysis appliance. That's Blue Code Sandbox. We choose it because it's our own product, and we at the same time test it and make sure that we find problems before the customer sees them. You can also use Cuckoo Sandbox. You can use FireEye if you want to. And the advantage of MAA is that we have an rich API, so everything you can do with the sandbox can be done through the API. So integrating that the whole sandbox was easy. Scaling, and just buy more hardware, put it next to each other, and make sure that there's a round-robinish distribution of the sample. So the ecosystem we have right now, it's fairly straightforward. We have feeds of samples coming in. We feed it in a system called Sample Workflow, which I'm going to introduce in a second. Then we have our sandbox cluster, so the MA or your Cuckoo Sandbox, whatever you would choose. We have a cloud bridge. The problem with sandboxing is that you create a ton of data. So every sample downloads additional samples. They create hundreds of events. And we first try to keep everything locally in our offices, but then we quickly run out of disk space, and operations was complaining that we're using up too much of the sample space. So we had a bridge into the cloud, so everything is now in Amazon. And we had a big database, because obviously you don't want to just create and store the data, we also want to query it. So nowadays, our analysts have a database where they can query every single event that ever happened inside our sandboxing solution. Sample Workflow is basically the pre-filtering and decision-making engine for us that makes sure that we run only samples that are actually interesting for us to be executed inside the sandbox.
Multiple sources flow together. So as I said before, we have cooperations with other AV vendors. We have our crawlers that go for the public known malicious domains that produce or drop samples, and we have VirusTotal subscriptions. So they all flow together. We have to make sure that we store the samples and make them accessible for the sandboxing solution. Then we have a chain of workers, where every worker gets more and more expensive, that analyzes a sample for different aspects. So the first worker could be, for example, a hashing worker. So we get a large array of different hashes, and we check if any of those hashes are known to us. The next worker could be an AV engine. So we scan it, we extract the static information. So if the sample may be signed, we get the signature of the file. We can check the signature if it's a trusted or a real signature or a fake signature. And the deeper you get into this chain of different workers, the more expensive it gets when it comes to CPU time, but also execution time. And sometimes you cannot decrease execution time by just increasing the hardware. So the deeper you get into this whole system, the more information you collect about the sample, and the more metrics you get about the sample that allows you to make a decision if you want to run it in the sandbox or not. And only at the very end, when we know, okay, this sample was never seen before, AV has zero detection, or at least the detection is not confident enough, so maybe some behavioral detection, or maybe some of the AV engine detected, but others don't, and those who detected it, we don't really trust the detection. Then we decide, okay, put it in the sandbox and execute it for X amount of time. X amount of time, we have some heuristic values that gives us a execution time over the amount of information we collect. So we have a sweet spot where we can roughly detect 80–90% of all the samples. But then there's always a couple of samples. If you run this longer, then they will do more, they connect to more IP addresses, they will probably send out more spam, so different patterns will hit in the future. Right now, the whole sample flow system is built in a way that you can plug in new things. So if an analyst is interested in, I don't know, I want to have it as a steep hash of the file, then he plugs it in as a steep worker. He has to define by himself how expensive it is, so he picks the location of the SSD worker. And he updates the decision maker about the scoring of the SSD worker. So if the SSD worker gives him a steep hash and we see a similar SSD hash, the analyst has to decide, okay, if the similarity is higher than X, then we consider it to be known in a certain family, and we don't run it in the sandbox. All the data that comes out of sample workflow, and this is not part of the sandboxing data, all the data we get ends up in CloudWatch. That's the Amazon logging magic. We have some time database, so we see metrics, simple metrics, so we see what's going through, where things are getting slower. And then we started having some probabilistic databases. That's basically very cheap storage for trends. Everything that we use is either part of Amazon services, or is open source, or we write some stuff by ourselves, but mostly the clue in between. So the whole chain right now looks like we have our sample workflow where everything comes in. Then we have an HTTP API entry for the queuing system around our sandboxing system. For queuing, we use Redis queue. It's very simple. It works in memory. It requires a couple of lines of code to get it running. Then the queuing feeds the sandboxing cluster. Then we have Bifrost. Bifrost is the bridge between the world and Asgard, and the whole system is called Asgard, so we call it Bifrost. But Bifrost is a bridge that shoves everything back into the cloud. And then the data that comes out of the sandboxing cluster ends up in Elasticsearch. We have a big cluster, and we have a UI on top of Elasticsearch that allows the analyst to do queries in a query language defined by us to search the database for indicators that they deem to be interesting, and they can find relations between samples based on those indicators. So we have a big queuing system around our sandboxes, because we figured quickly out that filling up one sandbox with thousands of samples
is going to make this sandbox really busy, and we have no control over how long those samples are going to run and how much load it will put on the box. So we have a couple of queues around the MA boxes that make sure that we control really carefully which sample goes when to which MA box. And we also have the ability to, right before we execute the sample, update how long we want to run the sample inside the sandbox. And as I said before, the runtime of the sample has an impact on the detection rate of the sample. This whole ASCART, so there's the MA cluster, got a nice UI on top of it. I have a couple of screenshots. They're intentionally not really readable because I'm not supposed to show a lot of numbers. But the point is we have some control over the size of the cluster, how many instances are running in there. We see how big the queues are, and we see how every single instance is behaving, if they're having good throughput or if their throughput is currently low. And if the throughput is low, we can investigate, okay, maybe there's currently a sample in there that creates a lot of events, so the post-processing inside the sandbox takes a lot of time. So this is just an indicator for us and a high-level overview of what's going on. There's none of you, intentionally again, very small, so you cannot really read it, but I'll explain roughly what's going on. So in the top graph, you see the things that are coming in, and there's a description of the different graphs, what they mean, and it allows us to see, okay, are we filtering properly? So there's a couple of indicators of what we filter and what we don't filter. And at the bottom, this is actually the magic IDs of the files we are seeing. So as you see, there's usually this green line in the bottom graph, that's the executables, the generic executables that you see all the time, as usually viruses. And then there's this peak of a different file type. And this is what happens when you subscribe to random sources of samples. And if I remember correctly, this was a couple of HTML files. Because some crawler was downloading samples, but for some reason, instead of getting samples, he was getting HTML files, and he still considered those HTML files to be samples and submitted them to some virus total. They could be malicious. I mean, it could be some JavaScript, some buffer overflow stuff, some exploits inside the HTML, but usually it's just some problems in some crawlers. But this, again, shows us, okay, something is going on, and that probably has some impact on whatever happens inside the MA cluster. So some things you might have noticed in the previous slide, we are skipping stuff. If you look at the names of those families, those are all virus families, and if you know those families, you know they have something in common. So those families are usually known to infect other files on the system, so we call them file infectors. Or they could be ransomware, so they encrypt a lot of files. Encrypting a lot of files and infecting a lot of files creates a shitload of file operations. So they're going to read and write to files, and that creates a lot of events, and that makes the whole system slow because we have to store those events. That's really expensive. We have to index the events. We have to analyze the events. We have to pattern match the events. And all those viruses, they are known families. I mean, we want to skip them. We don't want to spend a lot of time and resources on executing them inside the sandbox. So the sandbox runs now, has a couple of samples to execute. What do we get out of it? First of all, we see the sandbox fail on some samples. This is really valuable information for us because either the sample failed because it was expecting something inside the sandbox that was not there, or there's something inside the sandbox that the sample decided to be an indicator that something is weird and it shouldn't probably execute inside this environment, or our system fails because we are humans and we write code that's not always perfect. So we detect things that go wrong, and we use those things that didn't work as we expected them as a task creation. So we updated the sandbox, we fixed the environment, we customized the environment in a way so the sample will execute in the future. We test performance, so how are we performing with certain file types, how we are performing with certain families. So as I said before, there's families that put a lot of load on the box, there's some families that are just dropping in another file, or families that open a backdoor that's super easy, that's simple, that creates a handful of events. We do a lot of monitoring automation around it that helped us to build a user story also for our customers who are interested in this kind of setups. So now we have this huge database with a lot of events. What are we doing with those? And basically, our analysts, they go into the database and they see, okay, there's a couple of samples, they showed a certain behavior, but we had no detection for those. And then they pivot from those events and see if there's similar samples that got a detection and showed the same behavior. Then they have the ability to cluster those together, and they can make detections that cover all of them. So an example for this could be a sample drops a file, and the file is malicious. Another sample drops a file, puts it in the same folder, in the same subfolder, or gives it the same file name, but the sample is not considered malicious because we don't have any detections for it. But the similarity between those events allows us to put the two files in the same group, in the same family. We can see if there's more similar events that put them into the same group. And then we can make a pattern that puts them together in the same group and have detection for them in the future. Another thing we do in our sandbox cluster is we run clean files. So clean files are files that are either directly scraped from an operating system or are files that are on whitelists that are maintained by various AV vendors. So you run those clean files, you look at events, and you make sure that your patterns don't hit on those events, because that would mean that we would flag this file as being malicious. But at the same time, we also learn about what are the events that are always there, so events that are a kind of a baseline in the system. We can look at how this baseline matches between known clean files and known malicious files. So I already mentioned that we have this huge amount of samples, we have this huge amount of events produced by those samples, and we push everything up into the cloud. And in the cloud, we have this big Elasticsearch cluster. Right now, we have 10 nodes from one of the bigger, heavier machines from Amazon. And we have this large amount of data, and we want to obviously tokenize them, index them, and make them searchable. So Elasticsearch was for us an easy choice in this case, because it allows you to quickly search across a large set of data. Right now, the numbers are kind of outdated, but we have 1.2 billion static and behavioral artifacts. So artifacts are whatever we collect with our drivers inside the sandbox, or what we have collected using static analysis on the file. So all those artifacts are collected for every single sample we execute, and then put into the Elasticsearch cluster. We have executed roughly about 60 million tasks. So a task is an execution of a sample in a specific environment. And we execute every sample in as many environments as possible. So in our case, it's usually a couple of Windows versions in different configurations, so with different applications installed, different user traces on the system, and we have a couple of plugins that control how the system behaves while the sample executes. Currently, the system is indexing about 80 documents per second, so it means every second we produce 80 new tasks and reports, and they get shoved into the Elasticsearch cluster. We have multiple risk score calculations, and that's something you always have to keep in mind, that just because you have a risk score of 10, that means the highest possible risk score based on a AV detection, doesn't mean that you have basically understood the sample, because it could be just because the AV detection was very generic, or it was maybe a false positive, or they grouped the sample into the wrong family. So we usually strip away AV detections or detections that are potentially generic, and we want to look at the detection based on pure behavior. So we have multiple risk scores based on different categories of events. So we have pure behavior-based risk scores, we have risk scores based on static information, and we have risk scores based on multiple different types of events. So what we produce every day is roughly 500,000 of tasks per 24 hours. As I said before, we have 2 different Windows operating system configurations that varies from time to time. We have our emulated sandbox, and emulated sandbox is basically a rewrite of Windows. That sounds very big, but it's actually only implementing a couple of APIs that allows to execute a sample to a certain degree. So it allows us to run a sample in only a couple of seconds and see things like starting processes or injecting into a different process or using certain APIs. And sometimes the emulated sandbox has enough events, enough information from the sample in only a couple of seconds, behavior events, not static information, that allows us to have a detection on the sample. So usually we have to have the emulated sandbox first, see if the verdict is good enough for us, and if so, then we don't execute it in the virtualized environment. But if not, or if you're really interested in the sample because we have no additional information where the sample belongs, then we execute in the virtualized environment. So our profiles in which we execute the samples are customizable. So that means you can boot up that VM, you can connect to that VM, and you can install software. Obviously, if you are a malware author and you execute in an environment, you could check for all kinds of different hints of if the system is actually used, if it's a virtualized system, or if the system is a sandbox. Easy hints are, is there something in the clipboard? So everyone copies things all the time, and so there should be something in the clipboard. Is there something in the trash bin? Obviously, some people delete stuff, so the trash bin, I mean, nobody's emptying the trash bin every day. So there should be something in the trash bin. Is there something in document history? So in all Windows versions, if you clicked on Start, there was a recently used document. So this kind of information is something malware authors are looking for to identify if this is a real system or not. Then if a system is up and the sample executes, they could also look for movement of the mouse, clicks, interaction with the sample. Some samples are smart enough to show you a dialog. Are you sure you want to install the software? And you have to click yes. If you don't click yes, then the sample doesn't do its malicious behavior. So all this kind of things can be configured in the virtualized environment because we give you full access over the environment. So for example, if you have a file type that's very unique or very special and it's usually not supported by default Windows, you can install an application. So if you have internal file type, an internal tool to open that file type, you could install it inside the virtualized environment and analyze those files too. Every task gets encapsulated in something we call the Malware Analysis Appliance Archive. This is the archive containing everything that was produced by the sample inside in the virtualized environment. So that means drop files, PCAPs, the detections, the events, everything is in one container. The container gets uploaded to Amazon and is accessible for all our analysts, so they can do big MapReduce jobs across all the containers. Say, give me all the samples that contain this specific event and run this specific tool over the samples or execute them again inside the sandbox. We also created STIX reports, so if anyone here is interested in STIX, the structured data sharing format, we create them. We create, again, roughly about 500,000 of STIX reports every day. We try to share them, but there's no real receiver out there who can handle this large amounts of data. But if you're interested, we have a couple of buckets on Amazon with STIX reports. Most of the work we actually do inside Amazon is using Lambda. I don't know if you've heard about this service from Amazon before. It's basically you pay for the execution of your tool, and if the tool is not running, then you don't pay for it. So it's not you're spinning up an EC2 instance and a VM, and you run your tools over and over again, but it's just executing the tool, and when it's done, it's done, and you pay by the millisecond. So we spend quite some time in those Lambda functions to execute and analyze samples. The lessons learned is that you have never control over the incoming data. You have to keep that in mind. And have an eye on the incoming data because the data will change and you have to adapt to what kind of samples are coming in. Dynamic scaling because the amount of sample that's coming in is going to scale. The amount of samples that are not detected by AV is always scaling up. So you have to be able to scale up your whole environment. Storing data was a big problem for us in the beginning. We used different technologies from Amazon, and in the end ended up using S3 and just doing HTTP push for the samples. Abstraction being far away from the actual appliance. Everything should be controlled with a couple of clicks in a UI. And finally, the hardware that you use. The sandboxes are running under high load all the time. So picking the right hardware that is able to handle this kind of load was crucial for us. Okay, with that, I'm finishing my presentation. Thank you for listening in. If you have any questions, ask them quickly because you're holding back everyone else from lunch. Thank you.